Hello, welcome to another video. So in this one, what we're going to talk about is we're going to talk about units and other introductory examples. So the first example that we're going to do, so example 1, okay, and these are the type of examples you'll see when you're doing homework and things like that. Let's go ahead and blow this up. Let's go to 20. We want to know how many kilometers are there in 5 meters. So what we're going to do is we're going to use the system. So we want to know how many kilometers are there in 5 meters. So we need to convert to kilometers. And we don't know this number. Okay, so that is unknown to us, how many kilometers that is. So when you're looking at how to do these types of questions, step 1, start with the number you know. So we know 5 meters, and so we would put 5 meters right here, okay? And this right here, how this works, this grid system, is if you're going left to right, you multiply across, and up and down is division. So left to right is multiply, up down is divide. And our goal is to convert meters to kilometers. So the next step then, step 2, cancel meters and then put in the unit conversion for kilometers. Okay. So I know or have memorized or have looked up that 1 kilometer is 1,000 meters. So we put this into the grid. Okay, so we have 5 meters, and we need to cancel meters, so we'll put meters down here. And we put that unit conversion here. So 1,000 meters on the bottom, 1 kilometers on the top. Next, so this is step 3. Next, we divide and multiply. Okay. So we do 5 meters, 1,000 meters on the bottom, 1 kilometer on top. The meter cancels. Meters over meters is just 1. It's unitless. And then we do, so this equals 5 times 1 kilometers over 1,000. So this yields 5 over 1,000 kilometers, or 0.005 kilometers with the prefix. Okay. It should be noted that to do this properly, you need to know the conversion. And because everything is scalable, like what I was talking about in the other video, the conversion between meters and kilometers is pretty easy to understand. You just need to look at the prefix table, okay? Or understand that there's 10 to the 3 meters in 1 kilometer, right? And so if you understand that, anything that works up and down that table based on powers of 10, you should be able to do. The more complicated conversions require you to know it. Now in an exam, if it's a more complicated conversion, I will give it to you. I won't give you anything between meters, kilometers, centimeters, millimeters. Anything in that table that we talked about, I won't give you. I expect you to know that. But anything else, you should be able to figure out and can do on your own. Okay. Let's go ahead and do example 2 and look at an example of a more complicated conversion. Okay. So here we go. Let's go ahead and make this bigger again. You can actually read it. So there are only 14 peaks whose summits are over 8,000 meters above sea level. They are the tallest peaks in the world and are referred to as 8,000ers. What is the elevation in feet of an elevation of 8,000 meters? So we need to convert 8,000 meters to feet. There's 2 ways to do this. Direct meter to feet, or we can do meter to centimeter to inches and then to feet. And this is the path I'm going to take for more practice. So okay, so we're going to go meters to centimeters first. So meters, so 8,000 meters. And then in 1 meter, there are 100 centimeters, okay? If you're going from larger to smaller, you'll have more. If you're going from larger, or from smaller to larger, you'll have less, okay? So cancel out the meters, multiply 8,000 times 100, and what I get is 800,000 centimeters, or 8 times 10 to the 1, 2, 3, 4, 5 centimeters. If you need any assistance with scientific notation, just let me know. But in general, if you're going to the left, it's a positive number, and it's the number of times you're shifting, right? So we're shifting 5, 8 times 10 to the 5th. If you're going beyond that, okay, and you're making the number smaller, it'll be less than, okay? So if there's like a decimal, like 0.01, right, and you're moving to the right, so 0.01 would be 1, 2, 1 times 10 to the minus 2, because you're moving to the right. It would be negative, okay? But if you have any issues with scientific notation, let me know and I'll try to help you out. Okay, so, and then large to small equals bigger number, like we got here, okay? Bigger number. And then if you're going from a small quantity to a large quantity, that would be a smaller, okay, number. So anyway, next up is centimeters to inches. Now, I've actually memorized, of all the, I never memorize anything, but this is actually one conversion I have memorized. I don't know why, but I actually have. And the conversion between centimeter and inches is 2.54 centimeters per 1 inch. Why have I memorized that? I have no idea. These squiggly lines here actually means approximately. Okay, that means I've done some rounding. But this is 314,960, so 314,960 inches. Okay. And again, a weird conversion like this, you would be given on an exam. Okay. But any of the other conversions, like meters to kilometers, you would need to know. So now the next one is inches to feet. So we write our astronomically large number here, which is stupid to deal with. We write inches, and then in the conversion between inches and feet is actually in 12 inches. There's 1 foot. Okay, so inches cancel. We're dividing. This is approximately 26,247 feet. You can do this also in one calculation. So right, where I write 8,000, then a 1 meter, there's 100 centimeters. And then in 2.54 centimeters, there's 1 inch. And then in 12 inches, there's 1 foot. And then these cancelizations or whatever would still yield 26,247. Okay. So that's how you do a problem with a more complicated conversion. Okay, so next up on the list, example 3. And we're still working with units in this particular type of example. But what we're worried about here is we're worried about how do you convert squared units, okay? So you have seen a nice apartment whose floor area is 880 square feet. What is its area in square meters? So we need to convert 880 foot squared into something meters squared, right? So we put in our unit right here. And now, since we're converting something that's squared, we actually need to divide by a foot to meter conversion multiple times. So the conversion I'm going to use this time is I will just use the direct conversion between meters and feet. So 1 meter is approximately 3.28 feet. So we will write 3.28 foot to 1 meter, okay? But now if we divide that out, feet squared over feet will just give us feet still. So we actually need to do the conversion twice. Okay, and now these two will cancel out that, and then we'll get, this is approximately 880 times 1 meter times 1 meter over 3.28 times 3.28. Okay, I guess I'll throw in the feet squared just so you can see that act. And so now this allows us to cancel these units and give us our meter squared units. And this is approximately 81.8 meters squared. Now, you would have to do this if it was cubed, like you were talking about a volume, you would have to do the conversion 3 times. Or if you're trying to do to the 4th, you'd have to do it 4 times, or to the 5th, 5 times. Okay. So keep that in mind. Okay. Man, we were just barreling through. Yeah, the first chapter of the book and the getting ready for physics part, the problems aren't too long. Okay. But we need to cover this stuff before we cover the more complicated material. So before we get into what our first topic is, which is kinematics. So, example 4. Where the posted speed limit is 55 miles per hour, what is the speed in meters per second and in kilometers per hour? Okay. So what we need to do for something like this is we need to convert two units at once. So for part A, it's 55 miles per hour into meters per second. So something in meters per second. So we need to convert miles to meters and hours to seconds. How do we do that? Well, I'm going to write 55 miles, and then on the bottom, I will write hours, okay? And then we'll be able to convert that. So the very first thing we're going to do is write the conversion from miles to meters. So in 1 mile, there are approximately 1609 meters. So again, those would cancel, and you would need this conversion, which I would give you. So now we've gotten rid of miles, and we're left with meters. Great. Now we need to convert hours into seconds. So I would put hours up here this time instead of on the bottom, because the hour now would cancel. It would divide out if I put it here. So in 1 hour, there are 3,600 seconds. If you don't want to do it that way, you can do minutes. So in 1 hour, there's 60 minutes. And then in 1 minute, there are 60 seconds. Either way, because 60 times 60 is 3,600, you'll wind up with the same answer. So if we do this, we do 55 times 1609 over 3,600. And this gives us roughly 24.58 meters per second. Okay. Now part B, we wanted to do 55 miles per hour into kilometers per hour. So this is a similar question. We start off like we did before. And so we would convert miles into meters and then into kilometers, or we could do miles directly into kilometers. And so 1 mile is 1.609 kilometers. Again, you would have to look that up. Miles cancel. This gives us kilometers per hour, so we're good. We don't need to cancel anything else. And this yields roughly 88.5 kilometers per hour. Okay. All right. So that's all the type of unit conversions you'll see that you need to get your head around. Okay. It's very important to be able to do unit conversions, not just in this class, but in life in general and future careers. You know, people have died because they've gotten the units wrong, or projects have broken. I remember for my project, it was extremely important to get the proper units. And oftentimes the units seem arbitrary or not real, or they're hard to grasp. So it is often complicated, but it needs to, you need to know always what unit you are working with at all times. It's extremely, extremely important. Okay. So, example 5, we're working with sig figs, and we want to know how many sig figs are in each of the things. Well, for A, there's literally just one number, so it's one sig fig, right? In B, there's no zeros. All of these are significant. This would be 3. In C, I'm invoking the rule where the zeros aren't in between or anything like that. 7 is the only significant digit there. In D, 500, there's no period or anything like that, so these are all trailing zeros. That would make 5 the only significant. I'm just going to make this even. That would make 5 the only significant digit there. And then 0.700, because they're trailing 0 and they're after the decimal, not before, like in this example, this would be 3. For this one, 2.0, you are writing 0.0. You are intentionally doing that. That means that you know more about the system, so you're being super accurate. So you would say 2. Okay. Okay. Kind of a short little example, but that's how you work with sig figs. You just follow those 4 rules in the previous lecture, and you should be set. Example 6 is up next. And we're going to do a mathematical example with significant figures. Okay. So your measure, it's a long problem, so let's read through it. You're measuring a box and measure the length, width, and height, but unfortunately, it was measured with 3 different measuring devices. And so each one's going to have a different accuracy. So you report a length of 300 centimeters, a width of 300.5 centimeters, and a height of 300.75 centimeters. And we want to know, oops. How did that? Anyway, I don't know how I copied all this extra stuff. Okay, so we want to know what is the volume with the correct number of sig figs. Okay. Oops. So you're measuring it. We have these 3 length, width, and height numbers, and they're all different lengths, right? So they all have a different number of significant figures, and we want to know what is the volume. So volume, if you guys remember how to calculate volume, volume in general is length. I think length is typically represented by script L. So length times width times height. And you write that out. So we have 300 centimeters. That's a really bad M. 300 centimeters times 300.5 centimeters times 300.75 centimeters. And if you do this, you know, what I ended up writing is 27112612.5 centimeters. So, would you write this as your final answer? Not in a lifetime. So, not your final answer. And the reason for that is you have this guy 300 centimeters with 1 significant figure. So you have a value with 1 sig fig, which is 300 centimeters. That means that this is the least accurate, or the least, the least accurate value. And so your final answer can only have one sig fig. So round that answer up to 3, 0, 0, 0, 0, 0, 0, 0. So it is 30 million, okay? Or 3 times 10 to the 7, whoops, that's not 10, centimeter cubed, okay? This is your final answer. And this has 1 sig fig, because this is how certain you are about your answer due to the fact that you measured the length very poorly with a bad measurement device. So that's how sure you are of your answer. Okay. Next up is example 7. Okay. And this has to deal with estimation. Now, estimation problems are far and few between in this class, but it's still a useful skill to know. Because to estimate something, you kind of need some information about the system, which kind of ruins the point of estimation in the first place. So how do we do this? So you want to estimate the thickness of a book, or of a page of a book with 250 pages. And then you're told that the book is estimated to have a thickness of 1.5 centimeters. So thickness of each page should equal the thickness of the book, right, divided by the number of pages, right? So the number of pages have a thickness. That will result in the thickness of the book. The book is estimated to have a thickness of 1.5 centimeter. Okay, and there's 250 pages. So per page would be 6 times 10 to the minus 3 centimeter per page. Okay, that's the thickness of a single page, right? If you didn't have this estimation, if you didn't know, like you weren't able to do this, it would be really hard to actually measure 6 times 10 to the minus 3. That's a pretty small value. But you can always estimate something like that, right? If you know the thickness of the book and the number of pages. That may not be the actual value, but it's something. Okay, so the final type of problem we're going to do in here, or for this topic, is we're going to talk about how to determine if something is dimensionally consistent or correct. So we want to know, is the equation distance equals velocity over time dimensionally correct? Okay. Let me add a little more to that. If distance has a dimension of length, velocity a dimension of length per time, and time a dimension of time. Okay. So you should be told what the dimensions are if you're going to solve a problem like this. So how do we do this? So to do this, you write out the dimensions on each side of the formula as if you were writing an equation. So you write length, which is represented by these square, so this represents dimensions of length, right? So we're told length, so distance is length, equals velocity divided by time. Velocity, we're told, is length divided by time. So that would be L over time. And then is divided by time, which has dimensions of time. So now if we write that again, okay, so if we write that again, we would write length equals length over time squared, because we're length divided by time is length per time squared. Now, what you do now is you say, is this true? No. Length does not equal length over time squared. Okay? So this equation doesn't work. And so if you were coming up with an equation in your head and you were trying to see, does distance equal velocity divided by time? You could say, no, it does not. Okay? But the correct equation is distance equals velocity times time. So we would write L equals L per time times time. The times now cancel, and L equals L. Okay? And so it ends up working in that instance. Okay? Whatever your dimensions are on the left side, they have to be equal to the dimensions on the other side. You can also do this with units. Okay, so if I wanted to write meters, which is the units of length, equals meters per second, which is the units of length per time, times seconds, okay, the same thing would happen, and we would say meters equals meters. And of course, you could also do the just the letters that represent them. So M for meter, S for second, and it would look like this, and then the same thing happens. Okay. You'll often see me checking units. So this is checking units. Very important. You'll often see me checking units after I solve a problem to make sure that I solved it correctly. Because if I'm trying to solve for time and I don't get units of time at the very, I don't get seconds after I've solved the problem, something's wrong. And this is kind of your first hint of that. So physics is very interesting in that you kind of know when you mess up the problem because you're not getting the proper units. And there's other ways you can figure that out as well. And this is why people do this, okay? Because it's useful in determining the equation, right? Like, if I didn't have this equation, distance equals velocity times time, I then figured it out. Now, the other question you may have about something like this is, what about constants? Like, this doesn't tell us anything. There could be 10, right? It could be 10 times velocity times time, or 100 times velocity times time. You could have some constant there without a unit affecting it. And those constants, unfortunately, you can't figure out from this sort of system. It just gives you a general skeleton of the equation. It doesn't give you what the equation fully could be. So do be cognizant of that as you work through this. But yeah, those are the types of examples you should see as you're working through the first homework and maybe the second. And of course, units are always important. So thanks for watching. I hope it was helpful, and I'll see you in the next one.